Today we will be talking about running algorithms in a storage hierarchy, but before doing that I have a little announcement because I will do a Christmas lecture next week on Friday. So this week Friday is a summary lecture because Saturday is the exam. So Friday I will be summarizing part 1 of the lecture. Next week Wednesday we will be talking about so-called bitmap indexes and Bloom filters. And on Friday there's a Christmas lecture. And what I will be showing is a Christmas tree and what Christmas trees have to do with indexes. So this is not just a visualization, this is a real database index structure. And every element here corresponds to an important concept from databases. So the triangles, the snow, the candles, and all this lametta connecting the stuff. And you can even run an animation. There's also these balls that mean something in the database context. And so for the moment you won't understand what's going on, but I will explain each and every detail here on that Friday. And actually all of these concepts maps to concepts you already know about. So 1 or 2 maps to concepts you already know about. Some others are new, but reoccur all over the place. You will see them all over in computer science and data management in general. So that will happen Friday in a week, next week Friday. Just a little announcement. Okay, but today we will look at running algorithms in the storage hierarchy. And we started about that already a little bit last week because so far we ignored storage when thinking about algorithms. And now we know about the storage hierarchy and we have to factor in a couple of more things. What are the costs for I/O? What are the costs for reading? What are the costs for writing when designing algorithms? And I briefly went through that already. So when you want to understand what is the performance of an algorithm, there's so many things you can consider. Of course, you can consider what's called wall clock time. You start running the algorithm, you set a timer, and once the algorithm is done, you stop the timer, and that's the wall clock time, the runtime of the algorithm. But there are more sophisticated ways to measure performance. One is counting clock cycles spent. Another is counting the number of I/O operations performed, in particular for the algorithms we talk about today. That's important. And so many more. It could be a separate lecture in its own, actually. And this is the slide I showed already last time. So when you worry about performance of any algorithm, there's only 3 ways of analyzing 3 classes of techniques to analyze the performance of an algorithm. One is an analytical model. So any form of mathematical model could be a complexity analysis, could be a cost model. That's class 1. The second is simulating the algorithm somehow. And the simulation should focus on the performance, of course. And the third is an experiment. So you implement the real thing as good as possible, hopefully in a real database system, send some real queries and use some real data sets. And none of these methods is better than the other, but typically you will see that certain sub-communities of computer science focus on one particular analysis type. So the theory people typically focus on analytical modeling and do not do too many experiments. We focus a bit more on experiments, but in databases actually all of those methods play a role. And typically to get it right you should use at least 2. When trying to find out what is the performance of your algorithm, always use 2. Never rely on a single one. Never rely on, oh yeah, I implemented it and that's the result. No, that's not how it works. You should have at least 2 independent ways of determining the performance of an algorithm. And then you can also compare, do they match? Do my simulation results match with what I observed in the implementation? Does the complexity analysis I did for my algorithm has something to do with what I observe in real life? If that's not the case, so there's a bug somewhere, probably. This is an excellent book. I really recommend that. It's super old, but explains that in all detail. Okay, and we went through that already. So the trade-offs for the different methods. Analytical modeling, meaning, it's relatively easy to do, but it's far away from reality. However, it can be generalized like crazy. If you have an analytical model, if saying this kind of sorting algorithm has whatever average case n log n complexity, then no matter how you implement the sorting algorithm, in a programming language, the complexity is not going to change. That's going to stay the same, unless you implement it in the wrong way. Then it may happen. However, for an experiment that's more down to earth, and then the same algorithm implemented in different programming languages, implemented by different people, implemented on different systems, implemented on different storage layers, completely different ballpark. Nothing of that changes the complexity, but the wall clock time can be very different. Yeah, that's something to keep in mind because typically when people say performance, they focus on one of these three worlds. Okay, and now we think a little bit how to do these kind of things, how to implement algorithms in the storage hierarchy. And an important abstraction is the abstraction of using queues. Yeah? A sequence of items you put in a queue. You can insert something into the queue and then you can remove it. I split that up into reading and writing. So there's a read queue. You can read from that, and this is at the same time an iterator. So there's some next method, and you can basically use that in a for loop in Python. You will see how that works in a moment. And you have to be careful here because next is just showing you the elements that are currently in the queue. Pop is additionally removing it from the underlying queue. Yeah, those are the two ways of reading from a queue. Here you can always ask the queue, give me the next element, give me the next element. Maybe we can move already to the showing that in PyCharm. This is in, so I can go on, check out, yeah, false checkout, who cares? It's committed and pushed. So where am I? System interfaces, queues. So you see that here in the code we have interfaces and there's the implementations, but interfaces should not carry implementations. Sometimes an abstract class has a little thing here and there, but the main implementation is outside the interfaces folder. So there's queues, and here you will see a read queue. Yeah, if you go there, why doesn't this work again? So here we go. Yeah, so we have the next method. We have this next method. We have this pop method. We have a close. Close is there an order later on? You will see if I implement the queue based on a file, there should be a close method allowing me to free temporary files, stuff like that. On C++, you would probably need that to free memory or something like that. Yeah, so for all of these elements in a data processing pipeline, there's always a close method, because that allows you to garbage collect and free memory and stuff like that. That's all you need, yeah? Except there's also, we will see how, maybe we go to that later, but I can also set a constraint here. For this queue, I can say, okay, what is the memory you are allowed to use? That's also in the API already. Yeah, then there's also a write queue. So the write queue has an insert method where you can insert an element. It has a close method again, yeah, same as for the read queue, and it has a flush method. We talked about flush already multiple times in this lecture. So you have something in memory, and maybe you want to flush it down. You want to guarantee that the stuff gets pushed to the storage layer underneath. And that's what I'm modeling here. So the API allows for that. So in this lecture, I will focus on these two storage layers, main memory and SSD or hard disk. These two storage layers only. That's what we will be talking about. But the techniques I'm explaining and the implementations of the queue interface applies to all of the other layers as well. But let's focus on main memory and some hard disk or SSD. Once you understand that, it's easy to transition that to other layers. Yeah, the size call here, I have the set memory limit. We will get to that later on. Right, so, and then, so I have a read queue, I have a write queue, and then I have a read-write queue. A read-write queue simply inherits from both of those. It's a combined interface, an API combining the two interfaces together. You see that here, read-write queue extends read queue and write queue is still abstract. Yeah, that's all you need to know for the moment. Right. Good. And then the next up is, now we can think about, okay, how do you implement this stuff? And for the algorithms I will be showing today, it's a great idea to have a main memory-backed implementation and a file-backed implementation. Yeah, that's what I will be showing in a moment. So again, go back to what we have in mind. So I want to show you an algorithm that works somehow in the storage hierarchy and will somehow write data to disk. Will write data to disk, will load data from disk. And rather than implementing the algorithm directly, opening a file, writing to the file, closing to the file, I abstract this stuff away. I say, okay, no, this is a queue, right? Whatever you do with the queue, however you implement the queue, I don't care. And this in particular allows me to test the algorithm independent from the file handling stuff. I don't really care. Yeah? I just have the abstraction, the interface to the layer underneath to say, hey, that's a queue. Yeah? And if I implement the API with a simple list in Python, I can test my algorithm independent of the external memory fluff that may happen. Yeah, that's one of the tricks I'm playing here. So there are two implementations. One is a list queue, and the other is the external queue. Let's briefly look at that. So where am I? So implementations, again, are not here in interfaces, but in a directory queue. And here we have a list queue. Yeah, so it implements this read-write queue interface and also an iterator. This is redundant, I think, because the read queue is already an iterator, right? It's redundant. Yeah, could remove it there. But basically what you see is, okay, it has a list. Yeah? So when you call the initializer, which is kind of a constructor, there's a philosophical debate on whether the init in Python is the same as the constructor. We don't have to care about that for the moment. This creates the instance, initializes the instance, and also adds this attribute buffer. Yeah? And initializes this with a list of this object type, which is used as a parameter in the generics. Yeah, then everything you do is just, when you insert, you append to the list. When you want to iterate over the stuff, you reroute to this buffer. That's the iterator. If you call next on that, you reroute to the iterator. If you call pop, you pop from that buffer. That's all you do. Yeah? And the size, of course, is the number of elements in that internal list. That's my entire implementation. So it's basically just a wrapper over this list. Or I already have a queue. Problem solved. Right. And there's then also if there's a list implementation, there's an external queue implementation. Yeah, that's a file-based implementation. We don't have to go into the details, but basically, in the initializer, you create a file. It's a temporary file. There's an extra Python library for creating temporary files, so you don't have to worry about that. The stuff will be deleted. It will be put into some temporary directory with some file name you don't have to worry about. And everything else is details. Yeah? This is just making sure that I can write to a file and read to a file, and it behaves as I'm expecting a queue to behave, just that the data is backed by a file. Yeah? So I have these two implementations now. Right. And then the next, and then basically the inside is, or the trick when implementing algorithms in a storage hierarchy, in particular in between main memory and external SSD. When I say external storage, take it as an abbreviation for SSD or hard disk. So the trick is you implement your algorithms using this queue interface, abstracting away the notion of files and networks. Yeah? This is a trick that you can play in multiple places of the storage hierarchy. There are more tricks, in particular when it comes to making your algorithms efficient in the caches. Yeah, L1, L2, L3. There are other tricks you can play. There's an entire sub-community handling this stuff that's called cache efficient or cache oblivious algorithms. Yeah, you can do more, but here for the context of what we are doing That's all you need. And you see that in the test. Yeah? So there's a Q test. So let's look at that one. That's in tests. Test queues. Q test unit case. Should I dare to run that? So many tests being run. But this is the kind of pattern you should use in testing your stuff. Yeah? So here what I'm having is a Q factory. So a factory in object-oriented programming is just a method that I can call that returns an instance of a certain subtype. Yeah? So if you look at this type, you will see all this does is it creates an instance. Yeah? That creates an instance of type read write queue, and the objects handled by that read write queue of this type. Yeah? So that's a Q factory. If you added a second parameter to this, you could actually make it a generic factory for any class. Yeah? But here I made a specific Q factory type. So whatever I call that, and the implementation should return an instance, not an abstract, not the abstract class, but really an instance, a subclass of read-write queue. Yeah, that's the idea here. And this is very important because now I can inject that into the algorithm. So whenever the algorithm needs a new queue for whatever reason, it will not have a hard-coded decision, oh, it's always this queue. No, the algorithm will be calling on my Q factory to get a new instance from the Q factory. Yeah, that's an important trick here play. Yeah, again, this is a strategy pattern in the sense of a design pattern. This is called strategy. Strategy is another word for higher order functions. You have a function you inject into an algorithm, and the function is specified outside by the user. Yeah, it's all over the place, this trick, and it's so powerful, it's insane. Yeah? And this factory is just a special case of that. And then you see here in the test, oh, I loop over my different factories. Yeah, so I have two types of factories here. One is a list queue factory, and the other is an external queue factory. So I do 2 rounds of that. The first will be using the list queue factory. Then I do all kinds of tests against the interface, of course. Yeah, so I here get an instance of that, then I add stuff there, then I flush it, then run a couple of asserts. Now I read the data back, check sizes, tra-la-la-la, call close. Yeah, the stuff you do to test the queue. Yeah, but the test is written against the API and not against the instance. Yeah, that's very important there. And that also allows me to easily extend the test, because if I now write if I provide a third implementation of the interface, I just add a line here and I already have the test, because I have a test against the API, not against the specific implementation. I'm not saying that you shouldn't have specific tests. Yeah? You will see that the external queue, yeah, I think it's good enough for the lecture, but for product I would add a couple of more things. Yeah? And maybe you want to test these things in a bit more detail, but for this lecture it's enough, I would say. Yeah? Okay, so there we are. That's what I wanted to show. Any questions so far? Those are the building blocks I will be using for the algorithms. Yeah? So we have a queue abstraction. Queues will be used all over the place in external memory algorithms. So all the algorithms are phrased against that abstraction, not a specific implementation. How do you teach an algorithm to instantiate a specific queue subclass? You inject a factory. You give it a factory for instances, and that will be called. Like that, the algorithm can run on any type of queue implementation. That's a major trick that I'm playing here. Okay, so with that, let's look at a concrete algorithm. So external merge sort. This is an external sorting algorithm. There are more, but this is one of the most important ones. This allows you to sort arbitrarily large data sets, no matter whether the data set fits entirely in main memory or not. Yeah? This is, for you young folks, it's really hard to imagine, but there was a time when data didn't fit into main memory. That really was a time, hard to believe, yeah? Back then, those were the days, yeah? But sometimes data sets are like that. So sometimes there is a mismatch between what you can fit, and then if you, for whatever reason, want to sort the stuff, you're screwed, because quicksort and whatever heap sort, they don't work out of the box with such data sets. The cool thing about external merge sort is it already works with 3 pages of main memory. Yeah? If you have 3 pages, you can sort a petabyte of data. Will take a while, but it works. Yeah? So this is a very small constraint to the algorithm. That 3 pages, that's just like nothing, and you can still sort no matter how big the data set is. That's really cool. Yeah, this can also be adapted to sort in a distributed system. Yeah, as so many other algorithms we are talking about, there's typically little changes you do, and then you can do fancy stuff with that. And one is you can also do external sorting and distribute it over a network of machines. It's relatively easy. Again, the factories do some magic here. So you could have a queue that's not backed by a specific file on your machine. You could have a queue that's backed by a file on machine X, by a machine somewhere in the cloud. That's one part to the solution here. So why should we care about sorting? So actually, when I was a student, the professor explained sorting, and I said, okay, nice, that's boring. Why would I care? So I said, the pain comes up now. That's really, we went through all these 10 different main memory sorting algorithms: bubble sort, insertion sort, heap sort, quick sort, radix sort. Oh, what else? There's so many more sorting algorithms. Yeah? And it's important. I'm not saying you shouldn't learn these things. It's a good exercise also to understand how algorithms are designed and understand complexity classes and stuff like that. But the important thing about external sorting is it uses so many principles from data management and big data management, if you want to call it like that, that reoccur all over the place. So if you understand external sorting and can master external sorting, you shouldn't be afraid anymore of big data sets, no matter whether you want to sort them or not, because the principles and patterns in external sorting, you can solve so many things with these things. It's incredible. It's really, silver bullet in a way. So I wrote it down here. So if you master external sorting, you will easily understand and be able to master many other large data problems as well. That's why it is so crucial to understand that. And also, I will be explaining first a very simple variant of the algorithm, and then we can extend that in a zillion ways. There's so many tuning knobs and variants you can play. It's crazy. Okay, that was that slide set. Okay, let's switch to this other slide set. So external merge sorting. And I start with an example, and then I show you some pseudocode, and I will also show you the implementation in our system, of course. So I will make a walk through the algorithm using this example. And what I will be sorting is 8 pages of data. Each page only has 2 integers. Each integer has, doesn't matter how many bytes actually. So I'm just saying this is a page. Oops. This is a page. I have to switch the pen size again a little bit here. Hold on. So it depends always on the resolution of the slides. Like that. Okay. Here we go. So this is a page. This is a page of 8 of those pages, and they should be sorted. And the assumption is this doesn't fit into main memory, just to make the example small. So here we have an empty page, and this is a page that contains 2 of those integers in this particular order. So there's first an 8, and then there's a 7. Now, how do we sort that? So I will assume for the moment that I only have 2 pages at that point in time. Again, for external memory, for external sorting, you need 3 anyway, so could have done this for 3 as well, but just to show you, just for simplicity and also to make things add up in the merge tree later on, you will see why this makes sense. So I assume I have 2 pages. So this means to sort this, I will now read chunks of the input file one by one. So the algorithm in this phase fills the entire main memory with the data from the file. As much as you can fit into main memory, you load into main memory. That happens here. So you have 2 pages. Okay, cool. Then I can load these 2 pages into main memory. That's what I do. Then on these 2 pages, of course, you can run a main memory algorithm of your choice, whatever you want. Let's say quick sort. Yeah? So now you have it sorted, 2, 3, 4, 6. And then what you do is you write the stuff out into a new file. Yeah? This file is called a run in the context of external memory algorithms. But this is an external queue, of course, in our implementation. Or I mean, if you get rid of the terminology of disks and stuff like that, that could also be a list queue. Yeah? The algorithm works in the same way, no matter whether the queues are backed by disks or not. Yeah? So I'm writing out a queue at this point in time, or in the context of this file, I'm writing out a file that's backing that external queue. So I wrote out the file, a sorted sequence of those 4 numbers of these 2 pages, and now I proceed like that for the entire input file. Yeah? So now I free the memory, and now I can read the next 2 pages from the input file. Load them into main memory. Yeah, I abbreviated that here in the slide set, but then basically you sort these 2 in main memory. Yeah, and then write out the sorted sequence again to a run. This is a 2-page run. And you proceed like that. You do that for each and every 2 pages. You only have 2 pages. Now we're done. Yeah? Now we have these 4 input runs on disk. Yeah? Let's assume it's running on disk for the moment. This is phase or pass 0. So now we have these runs, and now I will recursively merge the data. And this is the limitation why you have 3 pages. So you have a certain number of input runs. Here in the example, it's 2 input runs. 1 wouldn't make sense. There's no merging if there's only 1 input run, obviously. 2, it's okay, you merge something, but you can have any number of runs. The important thing to keep in mind is for every input run, you need 1 page of memory. For the output run, you also need 1 page of memory, and that defines what's called the fan-in these algorithms. Fan-in, 1045. The fan-in is the number of input runs you're merging. The number of input runs. Input runs. Yeah? And if the number of pages I have a variable already for that here somewhere. I always mix up this. It's a small m and a capital M in external algorithms. Maybe you need to fix that afterwards. But let's assume that the small m is the number of pages available, number of main memory pages. Main memory pages you have available. Let's assume we define it like that. Then the maximum fan-in is what? What's the maximum fan-in I can use for a merge? 1 input page per 1 page for input run, and 1 page for output run. What is the maximum fan-in? Fan-in max. Blah. Is what? n-1, of course, yeah? Right. And this is a tuning knob. So it really depends on the I/O costs. Yeah? So you would assume, okay, I set it to the maximum always. That would give the likelihood increases that the merge tree will be small, yeah, and that I'm quickly finished. But that's not true. The truth is typically in between 2 and m-1. Yeah? So the fan-in is somewhere in between there, giving you the highest performance. It really depends on the storage subsystem. We can talk about that later. Just for the moment, it's important to understand this doesn't have to be 2, just only 2 input runs, and it doesn't have to be the maximum. Yeah, something in between. That's the tuning knob. So now I basically merge those that data file-based. So you can do that with a heap or any other priority queue. So basically now we have these loaded in memory, and now you can determine, okay, what is the smallest element? That's the 2, so you will put the 2 here. What's the next smallest? It's a 3, so you put the 3 here. Aha, one page for the output run is now full. You can write that page out to external disk. That's what happens in the next round. And you can also discard this one because all of these elements were now considered in the merge. So you load the next page into main memory from this input run. Yeah? This contains 4 and 6. And then again, you keep on merging. Aha, we have these 2 4s, we write them out. Aha, this page is full. Now you have to output that page to disk. Yeah? You cannot discard these 2 yet because there's still the 6 and the 7. Yeah? But then, okay, you write out the 6, so you can discard that one. You write out the 7, you discard that one. Then you have 8 and 9, you can actually directly copy over those pages to the output run. But then you're done. Yeah? And now you have output run which has a size fan-in times sizes of the individual fan-ins. It's the sum over the sizes of the input runs, of course, which happens to be times 2 here, of course, because I have 2 input runs only. Yeah, that's how you do a merge. Yeah? Is that merge clear? So it's really important to understand. It's an element in these algorithms. How do I write it there? So I write it bottom up, okay. So the data is coming in, and it's being merged here, and it's coming out. Yeah, and the idea is really, there's one page reserved here, one page reserved there. Again, a tuning knob could be to have more pages for the output. Yeah? It's a common trick you play. But that's all you need. And inside there's a heap that tries to understand, okay, what is the smallest? Yeah, if you have multiple inputs here, let's say something like that. Yeah, so the heap has to understand, okay, from all of those elements I haven't processed yet, from those pages, what is the next smallest element? And that next smallest element should be sent to the output. Yeah, and that's what you're doing. So you always, the heap gives you a pointer to the next smallest input over all input runs. Now that's the trick you're playing there. And then you merge until all the inputs are exhausted and have been written to the output. Yeah? Okay? Kind of, yeah? If you invert this, and that's why this is so fundamental. Assume I write it like that. It's a little bit like an electric circuit in a way, or a neuron. Is it a neuron? No, it's not a neuron. Today, everything is neuron. Okay. So let's assume data comes in here and goes out here. So I really rotated it by 180 degrees, right? This visualization, but what the heck is that? Which kind of operation is that? Data comes in. What should I write here in the box? Yeah, someone else? Huh? A split, yeah, aka partitioning. Yeah, partition. So based on some partitioning function, whatever, a hash function maybe, can be any partitioning function, you say, okay, I put stuff into different output streams, into different buckets. Yeah, so bucket 1, 0, 1, 2, 3, whatever the semantics is, that's partitioning. And that's the inverse to merge. Yeah? Merge is also related, of course, to union, but union doesn't preserve the order typically. Yeah? So here we have order, so we have back semantics. Yeah, but you can also do partitioning, keeping the order, of course, of the input. But just for you to say, this is the inverse. Yeah? And you see these two patterns all over the place. Either it's some sort of merge or it's some sort of partitioning. Where do you see partitioning and sorting algorithms? a very famous sorting algorithm. There is partitioning. At what point? Yeah?
Maybe at the point of dividing the input into smaller chunks.
Yeah, which algorithm does that? Main memory algorithm? Huh? Main memory merge sort? Yeah, no, I was thinking about a different algorithm. Yeah? Quicksort, right. Quicksort is doing that. Yes, you have the sequence of elements, and you pick a pivot with some strategy pattern. Yeah? And then you make sure that in the first recursion step, everything on the left is smaller, equal this stuff, and everything on the right is strictly greater that equal can be assigned to any side. And then you do what? You call quicksort on this and quicksort on that. Yeah? You recurse, the same thing. That's the recursive partitioning. That's all what quicksort is doing. Yeah? And then at the leaf levels, you can do other tricks and change the algorithm and stuff, but basically it's that, recursive partitioning. Okay, so this is a merge. Yeah? And now we can do that for level-wise. I'm doing it level-wise here. And I do it for these two runs, yeah, merge them into this 4-page run. Yeah? Now I'm done. I have these 2 4-page runs. Of course, I can throw away this stuff. The data is now replicated into another file. And now what's left is one other merge, again using the same algorithm. It's always the same algorithm being instantiated, merging the stuff into one final 8-page run. And there goes my sorted file. That's what I wanted to do. One sorted file that contains the data from the input file sorted in a file. That is what external merge sort, how it works. So it's relatively easy. Huh? So here's pseudocode for that, just to warm you up a little bit for the implementation. So we have this fan-in of the merge phase, as shown on the board. And the number of, yes, I got it right, it's a small m, good. So the number of pages available, determining also the fan-in or the maximum fan-in. And then we have these 2 phases. Yeah? So this is this run generation phase. Yeah? You always grab m elements of main memory and get the next m elements from the input R and append this to the heap. So I use a heap to manage the existing runs. You have to keep track of which runs did I generate already. Yeah, maybe because you later on have to merge them. So you have to be able to access those runs. And I do that in a heap here. Yeah? So once you're done here, you have the runs generated for the entire input data set. And then you basically loop over the heap until you end up with a single run. That's the idea of this simple implementation of external merge sort. Yeah? So you remove f runs from the heap. However the heap is organized, that's a different thing. Yeah? Let's mention it here. So they typically organize the heap by the sizes of the runs. The smallest run has the highest priority. Yeah, that's if you go back here. So you want to achieve a merge tree something like that. Before looking at the bigger merges here, you want to merge the smaller ones. So an easy, straightforward way to configure your heap would be to make sure, the runs having a smaller size are merged first. Yeah, and then that gives you a kind of level-wise merging bottom up if I rotated this. Yeah, now it's top down on the slide. Yeah, but basically start with the smaller runs, merge them into bigger ones, and so forth, and so forth, and so forth. Yeah, that's the idea here. Right. So you grab these f runs and then you merge them. At this point in time, I initialize one of these merge operators or merge algorithms, however you want to call that, and this will create an output run. I will add that output run to my heap. So these, let's remove some of the markings. So this, F input runs will be reduced or will be merged to one new output run. Yeah, so I remove F runs from the heap and add them back to the heap. That's what the algorithm is doing. Yeah, then I check again, okay, do I still have more than one run? Okay, it means I still have to merge stuff. Okay, let's go and merge the stuff. Yeah? So I keep on running until eventually the heap only contains a single run. And that is my final sorted run, the external file. Yeah? So far? Makes sense? Okay, then let's look at the implementation. Where's my Python? There's my Python. Oops. Come on. So implementation is in sorting, and maybe we start with a run generator. Yeah. So this is phase 0 thing. The input data is delivered by an iterator. Okay, we have a queue factory as explained. Why do I need the queue factory? Because the runs have to be written out somewhere to the output runs. So I have to have a queue factory. Obviously, number of tuples in main memory, that will be important. And you have to factor that into the generic algorithm already, even though you might be using list queues, because the algorithm must say, okay, you get that much of the resources and you get that much of the resources. You can abstract that even more if you want it. I stick down to not just the number of tuples, so actually here it would be objects, would be a better term, probably. Okay, then we do all of these assignments to attributes of that object, and then we create the runs. So how do we create the runs? So I have something that's called run metadata, and this stores the name of a run. Oh no, this documentation is broken. Oh, ignore the documentation. Fix docu. Okay, so what this does is it keeps, this is why is the documentation broken, because what did I do? I implemented it initially based on files, and I always had this terminology in my head. Yeah, maybe it's an interesting story how that happened. So I knew, okay, you have to show external sorting, and you have to, right? Okay, let's implement external sorting. What can go wrong? So I implemented external sorting, and then of course I started creating queues. I had the queue interface, I had an external implementation of that. I did the algorithm, and then I said, oh yeah, it would be really cool to show that it also works on lists. So the time you add the second implementation to an API, that is when it gets interesting. Because typically there's an overfit of your implementation to the API and vice versa. Yeah? So at that point I said, oh no, this is not going to work, this is not going to work, and this is not going to work. So actually I wrote a lot of code, I threw away a lot of code, then I discussed with a PhD student of mine who reviewed the stuff, and eventually we had the right idea how to do that. Because initially we did it in a way, and that's a typical thing you would see, is that you keep track of the file names created in a specific directory, would be one thing. Yeah, you give those, the algorithm assigns names and stuff like that, that's what you would do. And that is what was previously here in the run metadata. This is not here anymore. Now this is only the read-write queue, a reference to the API type, and the size. And that's what I will be using here in the algorithm. Yeah, so also this smaller operator I'm overriding here does exactly that. It reroutes to the size information given for the different queues here. I could also be calling the method here directly, but I replicated it here. Right. Yeah, so I create a list of those entries, and then so this buffer simulates the available main memory. And what I'm doing here is I draw from the input data. Again, this is the iterator, and I append to this list as long as there's memory available. So that is the break condition. So basically, I draw a number of tuples in my memory, many elements, and put them into the buffer. That's what I'm doing. Then I sort the buffer using the built-in Python methods. This can also use a different technique called replacement selection, second part of the lecture today. For the moment, this would be something like quicksort or something like that. Then I instantiate a read-write queue through the factory that happens here. And then I basically put all the contents from the buffer into that read-write queue. You could also imagine a bike load method or something like that, but it doesn't give an advantage here. Then I call flush on the queue to make sure if there's anything buffered inside that queue implementation, it's really written out to the disk. Yeah? So it's the same thing we had in the algorithm, in the example, if you go back here, here. Yeah, maybe this one. Yeah, so it's really writing out the stuff here to the runs. Yeah, so here my main memory is a list, a Python list. I fill it up with the individual elements from the input through an iterator interface. Once the list is full, yeah, as defined how many elements, number of elements in main memory, I've sent all the data to a queue instance I got from the factory. I write everything into the queue instance, say flush, and that would mean in an external queue, everything would be written out to disk. In a list queue, it doesn't have any effect, doesn't make any difference. So. And then comes this part where I collect the metadata. Yeah, so here I added to the list of runs I'm creating. Yeah, so I append a new run metadata instance, which has a reference to the queue I just created, and also collects the number of elements I put into the queue. Yeah? This is basically the call to queue.size. And also keep track of the number of elements being created. Right. So at the end of the day, you will have this list, the runs metadata, and that is also then returned by this method call. So we have a run generation result that's just a tuple. So I would highly recommend in Python, there's a tendency to use dictionaries as a workaround for types. You see that often in code. Okay, I want to return more than one element, then I use a tuple or a dictionary or something like that, but that's really not so readable and is error prone. So whenever I return more than one instance, I create a new type for that. And that's what I'm doing here. So I create this run generation result, and that returns a list of runs, wrapped in this metadata instances, plus the elements written in that run. Let me switch. Okay, so let's continue. Sorry, but, so the question is, so what's the storage requirement? So if you, you have it once already here, the input file, the orange pages, so to say. Now you created a second copy, where each run, the sum over all runs is roughly the same. Sometimes boundaries of pages and stuff you might be adding, whatever, but it's more or less the same size. And then if you enter the next, okay, you copy it over again. So, okay, you could replace the original file, for instance, then at most, now it gets interesting. Because then you could, so once you're here, you have double the size. And you could, if you have a mechanism to prune the file, you can always, like, for instance, once you created this run, you get rid of those pages. If that's possible on disk, and so forth and so forth. So there's always a slight overhead, but the overhead is here. You only double in the number of runs being merged. In the merge phase, it's kind of the same thing. Here you could, once you merged those into that, you can remove them, of course. That's the trick you could play. But it's not such a big, again, it's not such a big concern. If it's really large data sets, and then you really want to be careful. If you sort 1 petabyte of data, or do I need 2 more storage arrays or just 3, yeah? Maybe you want to fix this stuff, yeah? But yeah, cool, interesting question. Okay, but now in the algorithm we're here, yeah? Maybe I get rid of some of the markings again. Oh, that was previous. So in the algorithm we're here, in the code we're here. So basically this create runs creates the initial runs. So once this returns with this list of the runs being created, where's my QuickTime player? Here, then we're basically in this situation. Now we have these runs, we have metadata about these runs, aka queues, and now come the merge phases. And in the algorithm, this looks as follows. So we have this create runs method, and maybe let's first look at the test. Let's go through the tests first. Where's my test? Where's test sorting? Merge sorting test. Also here, test run generation. Right, here we go. So what do I do here? So I create a bunch of tuples, only 1,000 tuples here. So in writing these tests, of course, you want to make sure that the time to run the test is not so high. There's always this discussion in software engineering. So the tests to execute should really execute fast, yeah, but then you might have 90 tests where you increase all of the scaling parameters to be on the safe side. That's one thing you could do. So here I have this run generator that is creating such an instance of the run generator, passing my queue factory, and then I call this create runs method I just explained. And then basically I check sizes of the outputs, and I think I also check the elements themselves at some point. No, I don't. Okay, but then what I do is I do a merge. So in the code, the single stream merge is exactly doing this, what we had on the board. So a number of input runs are merged into one output run. And let's maybe first understand this single stream merge, how that works. So I have the list of run metadata. That's exactly the output I got from the first phase, from the run generation. So here's a list of runs, a list of queues. I have a queue factory again. I have these memory limitation we can ignore for the moment. Then I call this initialize heap function. And that is what I just explained. It organizes the runs, and no, sorry, I have to be careful here. So this points to the next smallest element in my input runs, yeah? Because they can be anywhere. The next element to draw, the next element to send to the output can be on any of those input runs. And that's what I'm doing here with this heap. You see that in the heap entry, so it has a queue, it has an iterator, and it has an object. So the object is the next element I draw from that input, and I use that for comparing. So this is how I overwrote the comparison operator. I want to have the smallest, so the heap is organized by the smallest element. And the heap has one of those heap entries per input run. Yeah, just the next element, which is by definition the smallest element available in the run, because the run is sorted in ascending order here. Yeah? So this is the smallest element. And that's what I initialize as a heap. Right, then I have all these run infos in this list. Yeah? So different runs generated in phase 0. And now I put them to the heap. That happens here. So this heap entry we just looked at gets initialized with this queue, and everything else is memory stuff we can ignore for the moment. How to assign memory in those merges. Yeah? Actually, there's more room here for a strategy pattern, but let's keep it simple. Yeah? So basically what this loop is doing is, okay, it's converting the input list to a heap. Then I call heapify on that list. So there are multiple ways to organize a priority queue. Here I'm using an array-based / list-based heap. How long does it take if you have an array of n elements to create the heap property? In terms of complexity, how many comparisons are necessary? Does anyone know? Yeah, so the heap is an array. You don't really have arrays in Python, so you have to have workarounds for that. And so forth, right? Was it like that? I have to think about that. Yeah, let's make it like that. So we have 7, 8, 9, 5, 22, 42, whatever, 70. So this is how the data sits in the array. Yeah, and that's how I represent the heap. Yeah. And then we have all these operations, bubble up, bubble down, and stuff like that. But the idea is in the heap, backed by an array, that this element has the highest priority. In our world, highest priority means that's the lowest number. So obviously this thing is not there yet. Yeah, to start running the algorithm, I first have to make sure that the data I put into this list, this is just saying this is basically linearized. This is basically saying, okay, this is list element 0, 1, 2, 3, 4, 5, 6. Yeah? I'll make a picture now. 11, 20. Before I ruin. So here's my heap. So the question is, how do you establish the heap property efficiently on that one? How do you do that? Yeah?
I think it should be n log n.
Mm-hmm.
It should be the same for mini as for max, so you just iteratively put the left element on the top, and then
Yeah.
you have logarithmically many layers, and then
Yeah, that's right. I claim it can be done in linear time. It's correct. It's a correct solution, but it can be done faster. Does anyone see how? You can do it bottom up. Just take the smallest of these three and put it on top. Yeah, so the smallest of these three is 7. So you swap 7 by 22. Recurse to this one. Smallest here is 5, 42. Smallest of that. What was it? 7 and 5, right? No, 7 stays there. 570. I think you have to go down once again. How was the algorithm? No, here the pass. Let's check invariance. 578, 5722. So the invariant of the heap should be that all elements on the pass are in ascending order, right? Did anyone attend algorithms and data structures? Should be? Okay, maybe I read back. Okay, but here, so if the algorithm does something like that, that's obviously wrong. So here you should bubble down it again. But I think you can do it in linear time. Maybe it's one bottom up and one down. Let me read again. Forget about that. But you can do it in linear time. Yeah?
I think for the real property, at least for max heap, in algorithms and data structures, this just means that for every layer, like for every horizontal layer, the items on layer X have to be larger, or in this case smaller, than the ones on the next layer below. So in this case, this would not be the case because 7,
Yeah.
for example, is larger than 9 and 32.
No, I mean, the heap I have in mind is pass-based. Yeah, so basically, so here we have a min heap. The smallest element is on top, has the highest priority. So here the pass property is preserved. Here it's obviously not preserved. You would still have to bubble this in either way. The problem now, however, is if you bubble this up. So I would suggest you take the smallest again. Yeah, 70 and 9. And then the path property is preserved. 5970 is ascending, 5942 is descending. I have to look it up again. I'll add a note to the slides because the bottom-up path is not enough. Anyway, okay, so you could create a heap there. Where are we? You create a heap with this method, and now you can use the heap in the algorithm. And that happens here in the next call. So this single stream merge is again an iterator. You see that in the test when you look at the test sorting, test queues, external queues, to close it. Test sorting, here we go. Here, so I initialize this merge and I can directly draw from that merge. Yeah, so this gives me the sequence of merged elements here at that point in time. I can directly draw in a loop, which is very handy for programming, of course. And that is the reason why in the implementation you have to implement the iterators. And the iterator. And what I do here is, here's the next method. Now I always take the smallest element from the heap. This is at position 0, because that is the next element to return. And then from this heap entry, okay, I draw the next element from the underlying iterator. And then I reinsert that entry again into the heap. Yeah, so it's always whatever is on top in the heap, I remove it, send it to the output, and then I have to add a new entry for the next element coming up from the queue. Yeah, that's the entire algorithm you're seeing here. This is done through heap replace in this heap queue library I'm using. Yeah. So you have to be careful that if the read queue is empty, so some of the queues will be empty while doing that, so you don't reinsert them on the heap, of course. Yeah, that's this condition. And then you return the value you initially removed here from this entry, the smallest heap entry. That's all that's happening. Yeah? So that's really the same what I already explained here on the blackboard. So this is what we are looking at currently, this heap, keeping track for each input queue, what is the smallest element? Yeah, then you draw here from, this is an iterator, so you draw from the iterator, which means it removes the top element with the highest priority, the smallest number from the heap and replaces it with the next element from that queue. That's the entire algorithm you're seeing here. Yeah? If you go back to our test, that's what you see here. And then I do a couple of checks here, back and forth. Okay, so far so good. Now we have these building blocks: run generation. We have a single merge operation now. How does external sorting look like in this world? So we go to sorting, external merge sort. In external merge sort, again, you have an input iterator of elements. You have a Q factory and these limitations, and also I pass a fan in here for the merge. And then there's this initial phase run generation. We call the run generator. The run generator returns this result we already looked at here. So again, the result is this list. Yeah, so the runs generated metadata for the runs handles to the queues representing those runs and the elements written. That's what's being returned here. Then write a couple of log entries. And then I initialize the heap used here. This is now a different heap. So be careful not to confuse the two. This is a merge heap I use to understand which of the next input runs are merged. This is, if we go to the pseudocode here, we had that here actually. So now we're looking at this heap here. Runs here. This is a runs heap, and now this is where I take the next f elements, and then I eventually will merge them. and then I add them to the heap. That's what we're looking at currently. So this tracks the different runs in the input. And then this method is exactly the idea, okay, I grab the next fan-in number of runs from the heap and merge them. So this is again this line of code here. Yeah? Pop k is called here. Let me remove some of the markings again. Yeah, this is what we're looking at. Yeah? You remove the next f number of fan-in merges from the heap, and then you will merge them into a new bigger run. That's what we're looking at currently here. Now, grab the next fan-in runs and merge them. So I pop as many elements as fan-in from the heap and append them to a list of runs to merge. Yeah? So I end up with a list of fan-in number run metadata instances. Yeah? So that's the next, those are the next runs to merge. So what do I have to do? I just initialize, that's what you see here, a single stream merge. Yeah? So for the same thing here. Yeah? For each of those merges, I can reuse the same stuff. I don't have to reinvent the wheel. So that's again a single stream merge being executed here. Yeah? You have factories, you have memories being set, you have the queue that was created by the instance here. You insert everything there, you flush the stuff, yeah, as seen before. It's no difference whatsoever. But of course, you create also a new run metadata object. That's now information about this output run, the merged run, the queue you just created. Yeah, you initialize it here accordingly and the size of that queue you just created. And now you push that to the heap. The heap push will make sure that the heap property is preserved again. So again, this is organized, highest priority is that run that has the smallest size. So you will end up with a level-wise merge. Do you have a question?
The number of runs on a certain layer is not a multiple of
Yeah.
the fan-in. Do we then have the problem that we accidentally merge two runs from two different layers already?
It doesn't hurt. You can do an analysis on that. Of course, I mean, with my textbooks example, it's always logarithm-based fan-in stuff, perfectly arranged. Reality is not like that. You can then tune fan-ins, for instance, to get back to the perfect merge tree, would be one way. Or you live with the fact that some of the input runs are smaller than the others.
But like, let's say we have nine input runs on some layer and we have a fan-in of two, so we can do 1, 2, 3, 4, 5, 6, 7, 8.
Wait, let's do it on the board. So 9 input runs. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay.
So we would of course go in pairs of 2 if we have that high. And then the question is for the ninth one, what guarantees us that we don't actually accidentally merge it with one of the 4 things that we already created for the next layer?
Doesn't matter. I mean, why would it? I mean, doesn't hurt the correctness of the algorithm.
They have double the size basically.
Sure, but that's how it is. I can live with that. So if I use a heap like that, basically I would now merge this one and that one, yeah, and then I would that one, and then again I have the same problem here. I mean, given if there's the same size, any of those, right? Yeah, but here now I have the same problem here because those are smaller than that. Yeah, I mean, a perfect merge tree you won't have. But as I said, what you can do is you can tune the fan-in to get closer to a perfect merge tree. And it gets more involved because at the end of the day, think about what we had in the undergrad lecture. It's about the total costs of the operation you want to minimize. So there should be a cost model giving you an estimate, okay, what is that going to cost? How long is it going to take? And you have tons of parameters to optimize. What is the fan-in? What is the memory assigned to inputs and merges? What is it assigned to outputs? How do I steer the fan-in? Maybe I change the fan-in in one layer of the tree, adjust it a little bit, and then change it back in the other to minimize RO or something like that. That's a long story. Yeah? Okay. I was here. Good. Now, so this basically now happens recursively. Yes, and you see there's this merge operation, external merge, that calls on this method. Yeah, grab the next fan in, runs, and merge them. So merges the stuff recursively for on and on and on. However, this is a different condition to the one we are seeing in the lecture slides. So I'm saying while the heap has more elements than fan-in, you do this stuff. You grab the next fan-in runs and merge them. In contrast, in our slides, we have this condition here. I say I keep on merging until there's only one output run left. Yeah, you see the difference? Yeah, so here I say I merge till the end until I have a file that contains all my sorted data. In the implementation, I say, no, not so quick. I just merge till then. And then I have any number below that still and runs that are not merged. And if I hadn't unveiled the solution to my question, I could have asked it. I hope you didn't read it. Why would I do it? For anyone who hasn't read what's in the... That's the downside of documenting every line. I should stop doing that. Or maybe there should be more versions. The undocumented code version before the lecture and the documented afterwards. So think about that for the next time we give this lecture. Okay. But conceptually, why would that make sense? So I only merge, and if you go back to the merge tree, yeah, that's a good example here. So rather than writing out this stuff here, I say, no, I stop here. Now I have my two runs on disk. Let's assume it's on disk, and I don't merge the stuff. Why? Why would that make sense? We'll give you a hint. It is an iterator. So the contract the external merge sort has to fulfill is, you get a huge input file, and then you call next on that iterator, the external merge sort iterator, so it should deliver the next smallest element, no matter how that is realized, but that's the only thing it has to do. Yeah? So what I'm doing here is called an online merge. So rather than relying on the underlying queues, which in an external merge sort would mean I would write out the stuff. Yeah, so that's what you see on the slides here. So if I executed this merge, this would mean, okay, I would read all of this stuff, all of that stuff, and would write it out to the file. And then, only then, the next call, the first next call comes into the iterator. And then I would be reading directly from this perfect 8-page run. So I would have spent once reading all of the data and once writing all of the data. But that is not necessary. So what I'm doing is I'm doing it online. The last merge is performed online, and that means I never write out this final file. Yeah, I don't do this stuff. I wait for the first next call on the iterator, and once that comes in, I have to find out, okay, where's my next element? Is it there or there? AKA, okay, I can initialize a next single stream merge. And then I set this to be the final merge, and I said, okay, I basically reroute the next call to this final merge in the iterator. Yeah, so you keep on drawing an external merge sort, and you see it here in the test again. Why does it always close my tests here? Don't have to understand everything. Test sorting. Yeah, when we test external sorting here, external sorting, tra-la-la-la, I call on this external merge sort. This is an iterator. I can use this in a loop, but actually I do a pairwise comparison. For each and every element returned, I compare it with a sorted copy of the data that I sorted in main memory to make sure it really returns the right result. And whenever I call next here, this happens implicitly here, when I loop over an iterator, internally, this last merge will determine what is the next element, yeah, and then draw it from that particular run. And that may also involve I/O. So while looping over the stuff, and only here, I/O will be triggered, if it's external queues, to read stuff from those second to last runs. Yeah, see that? Makes sense? Yeah, okay. Or should I explain anything again? That's my job, so show up. No? Okay. Yeah, so read, go through the code. Please look at that. It's really, yeah, you can learn so many things when talking about external sorting. And yeah, one thing we saw already here, replacement selection. There was a node, there was a to-do saying, okay, so I taught you the algorithm and saying, okay, you fill up all the available main memory, and then you write out the runs. This means the runs, the initial runs, have the size of the available main memory. That's trivial. But what if I told you there's an algorithm that creates initial runs that are bigger than the main memory? Create initial runs that are bigger than the available main memory. And that actually exists, and that algorithm is the beauty. It's called replacement selection. And it, of course, has a lot of impact on the algorithm, because here, if you have two main memory pages for run generation with quicksort, yeah, that's what we got. Yeah? We always have these two output runs. However, if you have an algorithm that creates, for instance, 4 pages with 2 pages of main memory, you have a high likelihood that the merge tree gets smaller. Smaller merge tree, less operations, less computation, less I/O to perform. So that's great stuff, yeah, if you have an algorithm like that. And this algorithm is called replacement selection. It's super old. Yeah, it's one of the marvels of computer science, actually invented by Donald Knuth. I think it's in his, so this is the Art of Computer Programming series, and this is in sorting and searching. So how does that work? So this doesn't make guarantees that the output is bigger than the main memory, but in reality, for real data, it often is somewhat bigger. So you get less runs, initial runs are bigger, and then you have fewer merges, hopefully. So here, the input is on the right, and I'm saying that I have 4 elements that I can put in main memory. And I'm sharing the memory between a heap and a list. So in a practical implementation, that means you have an array, if it were C++, and the first part is, or one of the parts, the first part could be the heap, and the second part could be the list. Yeah, they share the same array. Yeah, that's how you implement it in C++. Here I show it separately with 2 different structures. And on the left, you see the output run being created here. Yeah? That's on the left. So we work from right to left. Again, that's the property, so you never exceed main memory. Now, what you do is you start by initializing this heap. So you put that into the heap. Here, for simplicity, I sort the data. You don't have to fully sort it in the heap, of course, just maintain the heap property. That's fine, but here, for simplicity, now I have it in order. And now the algorithm proceeds as follows. It draws the first element from the heap, which is a 10, and it keeps track of what was the last element sent to the output. Yeah, in this case, it was 10. Now it pulls the next element from the input, and it finds out, oh yeah, 25 is greater than 10. That is fantastic, so we add it to the heap. This element is now sent to the heap, so the heap still has 4 elements. I can put it to the heap because I know so far I haven't output anything smaller than, so this element is bigger than the output 10 I sent so far. If it were smaller, it's a different case, but this is bigger than 10. So this means everything here is smaller 25, so it's fine to put it on the heap. So I put it to the heap, maintain the heap property, and here I am with my heap. So I continue with the algorithm. I remove the top element 20, send it to the output. Now I have free space again. Draw the next element 73. Okay, that's again greater equal 20. I put it to the heap. I remove the next element 25. Great, put it here. I draw the next element here. That's 16. 16 must not be put to the heap, because I already emitted elements greater than that. Yeah, 16 would be here in the sorted sequence, of course, so I'm not allowed to do that. Yeah, I have to put it to the side a little bit, but I cannot make it part of this run generation. So what I'm doing is instead I put it to a list. Yeah, so I decrease the size of the heap to 3 elements and add this element to a list for further consideration. Again, these two can be combined in a single array, because the sizes of those never exceed the available number of elements m. Okay, let's continue. So I draw 26, that's also smaller than 30. I'm not allowed to do that. So here again, you remove 30 now, yeah? So this will be changed to 30. When you draw 26, this is smaller than 30, you must put it to the list. As shown here, the heap shrinks to 2 elements, the list is now 2 elements. Next up is 40 to be sent to the output. Here we go. Now we draw 33. Oh, again, that's smaller than 30, will be added to the list. Next up, 73 to be sent to the output. Now we draw 50 from the input, again smaller. So we send this to the list, the heap is empty. At this point, the run is closed. Now I have one run in this example for this data of 6 elements rather than 4 that were available for main memory. Now I start all over. Now I copy all of these elements to the heap, establish the heap property, and I continue with the algorithm and create a new run. Yeah? Now you have to, of course, make sure that you start a new run and don't append it blindly, because the sorting would be violated. Yeah? So this must be separated somewhere. You have to signal to the outside, oh yeah, a new run is starting. Yeah? This is not the same run, it's a new run. And so forth, and so forth, and so forth. Yeah? Isn't that cool? Yeah, it's a pretty awesome algorithm. Yeah, like that you can create larger runs. So we haven't implemented it yet in our Python database. So I simply didn't find the time to do that yet. But it's one interesting engineering thing we could discuss. Okay, well, how the heck would you even implement that in this world? So we have an algorithm that spills out these different runs. And you don't want to materialize all of that stuff all over the place. So maybe you want to do that in an iterator world. How would you implement that with iterators? Yeah, what would the interface, how would an interface to a class replacement selection, how would that even look like? So I'm claiming there is a class replacement selection. I abbreviated a little bit, replacement selection. I say this is definitely an iterator, so it's of type, whatever, object type, whatever the elements are, we are sorting on, extending iterator, of course. And then what? But how do you do the signaling to the outside, right? I mean, how do you, it's not just creating a stream. For the single merge, if you look at the, here, in the single stream merge thing, there was an easy case. So it's an iterator of objects, right? But here for the run that generates multiple of those runs. Yeah?
Maybe you could return none at some point.
Yeah, the marker, that would be, yeah, so to signal, hey, by the way, no, that's none, you should start a new run, yeah, okay. Other suggestions? Yeah, but it's not so easy to see, but the idea would be to let the iterator return iterators, one for each run. That can easily be handled in whoever uses the stuff. Yeah, and that's also completely demand-driven, yeah, because you would draw on this iterator, yeah, you would say for it in RS, yeah, that is an instance of replacement selection. And then you would say for element in it, and then you would say whatever the Q instance you got to represent the run. What did we say? I think we said insert or something like that, yeah? Yeah? So basically a nested iterator. Huh? Yeah? Also for any kind of grouping operation or partitioning operation, that would be the way to go. All right, yeah, so much from my side. Again, Friday is a summary for part 2, Saturday is the exam. Wednesday, we will be talking about bitmap indexes and Bloom filters, and on Friday, I will be explaining what the Christmas try index is in databases. So see you then. Thanks.